So in essence, the relative comparison of K values will basically tell us how much or little product is actually being produced at equilibrium. Right? So if we look at something like this is a little bit on the extreme end, right? So we have a huge K value. So that tells us we have pretty close to almost product, like all product. Maybe this is like 98.8% product, right? We have lots of product in comparison to reactant. So remember the equilibrium is really anywhere between 1 and 99%. So you can have a super small equilibrium constant and it might only be 3% product, right? So essentially, let's say you had 5 different K values and you were asked to rank them based on percent reaction. You can do that because you know that the higher the K value, the more percent product there is going to be for that particular equilibrium. Okay, so temperature. So as I mentioned, temperature changes our K values, right? So you can have the same reaction over and over and over again, but if it's happening at different temperatures, you're going to have a different K value. Okay, so this has to do with, we're going to look at this more in the next lesson, but temperature is one of the factors that can influence an equilibrium. So meaning it can cause a shift to make more or less product, depending on the type of reaction that it is. So let's say we're dealing with this reaction here that's an exothermic reaction, right? So it has a negative delta H value. So that means if it were to go into the forward reaction, it produces energy, right? So meaning energy is on the product side. So if we were to increase the temperature of this reaction, what ends up happening is the equilibrium will no longer want to keep producing energy, right? So you've increased the temperature. It's not going to want to continue increasing the temperature. So actually what happens is the reverse of whatever change you end up making. So meaning if the forward reaction is exothermic, meaning energy is a product, if we were to start discussing the reverse reaction, remember, is read from right to left. That means that if the forward reaction is exothermic, the reverse of that reaction is endothermic, right? And vice versa. If the forward was endothermic, the reverse would be exothermic, because forward is producing energy. The reverse would be using that energy to absorb into the product to create our reactant again. So what ends up happening is if we were to increase the temperature, the rate of reaction would increase for the reverse reaction. It always will do, so when we look at the next lesson, this will make even more sense. An equilibrium wants to resist a change that is happening to it. So if the temperature that's being produced due to the exothermic process, if you add external energy by heating it up or heating up a test tube or whatever it happens to be in, it's not going to want to continue producing more and more energy. You've added in extra energy. So what it will do is it will shift gears to reverse the reaction to use up that extra energy that was just added in. So what ends up happening to your K value, you have to imagine the reverse reaction will begin to take over. It will be going at a faster rate. So what ends up happening is your products will become smaller because you are producing more reactants. So the reactant concentrations will go up, so your denominator goes up, and the product concentration will go down. So if you were to imagine going back to this one, I'm now going to have a larger number in my denominator than I had before. So what happens is the K value goes down. The K value is smaller. All right, so let's look at another example. Let's look at an endothermic reaction. Making C. And everything's a gas. A lot of 2 in front of here. Okay. So if the forward reaction is endothermic, right, to make C, A and B need to absorb a certain amount of energy from the surroundings. If it were to go in reverse, C would be making A and B and energy. So the reverse reaction would be exothermic. So if all of a sudden we were to add in energy, right? Geez Louise. Sorry about that. So we're going to add in energy. So what ends up happening is you're adding in energy to a reaction that is already endothermic. So what ends up happening is when you add in extra energy, it is going to push the endothermic reaction to go faster. Think about it. There's more available energy for this system to absorb to continue producing C. So what ends up happening is the forward reaction will increase in its rate and the reverse reaction will decrease. So my K value will all of a sudden have more product and less reactant. So therefore, the K value is going to go up. We're going to have a larger numerator in comparison to the denominator. So the K value will change. If you change the temperature, you're going to change your K value because you're going to have a naturally different concentration than you would have had before. Okay, so let's say we wanted to write a K expression for a reverse reaction. Okay, so anytime you are asked to write out the K expression, it is always written reactants and products, reactants and products being read from left to right. Reactants, products. However, sometimes you will be asked to solve for the K expression of the reverse reaction. So the reverse reaction is actually shown with a little apostrophe at the end of the K. So you have like KEQ apostrophe. That automatically means this is for the reverse reaction. So instead of having the products over reactants, it would be vice versa. And actually, this is the expression right here. It would be reactants over products. So you would have your N2 times your H2 to the power of 3 over NH3 to the power of 2. Now, let's say you didn't have these numbers. Now, let's say you didn't have any of this information. If you have a K value, let's say 10. If you had to solve for the K of the reverse, it's a reciprocal, right? So just like the K is products over reactants, and you were to write the KEQ with the apostrophe, it would be reactants over products. It's the reciprocal of one another. So solving for KEQ of the reverse reaction would simply be 1 over the forward reaction K. So this can be done, of course, with concentrations, or you can just simply do the 1 over K of the forward reaction as shown here. Okay, so we're going to take a look at a couple of examples of how you would basically use this K expression and what type of scenarios you're going to come across. All right, so let's take a look at what we have here. So it says, calculate the equilibrium concentration at 400 degrees Celsius of ammonia, okay? So we are looking for the concentration of ammonia at equilibrium, okay? And we have the reaction. And it says the equilibrium concentration for nitrogen is this, and hydrogen is this. And notice they said that those are the equilibrium concentrations. So this is our nitrogen equilibrium. This is our hydrogen equilibrium. And we're given what the K value is at 400 degrees. So since we have the K value, what we can do here is set up a K expression and simply plug in the values. Okay, so let's look at the K expression first. So it's products, right, over reactants. Everything is a gas, so everything is included here. And remember that the exponents are the coefficients. So we have the K value, we have nitrogen, and we have hydrogen at equilibrium, and we're solving for, my check mark wasn't working there. We are solving for ammonia at equilibrium. So we have everything we need except for ammonia. Okay, now common errors I see. So first of all, only things that have a concentration can go here. So meaning making sure that this is set up properly from this reaction is very important. Secondly, you have to make sure that the concentrations that are plugged into this K expression are at equilibrium. Okay, we will see what happens if they're not at equilibrium later on, but you must, if you're just going to use it straight up as is, the numbers you plug into here are at equilibrium, and that's important to keep in mind. Okay, so let's take a look. So we have everything except for ammonia, which is what we want to solve for. So we have 1.7 times 10 to the negative 2 is equal to our ammonia concentration squared over, we have our nitrogen concentration, 0.45 moles per liter, and we have our hydrogen concentration, and that is cubed from the coefficient. So our NH3 to the 2, right? So basically this is just cross multiplication. So if you take the 1.7 times 10 to the negative 2 times 0.45 times 1.10 to the cube, you end up getting 0.010182215. Okay, so keep in mind you're not going to round anything as you're continuing through. We only look at significant digits at the very, very end of our question. And then, of course, we have to take the square root because this is squared and we don't want square. We just want the equilibrium concentration for ammonia. So if we take this value and square it, we need 2 significant digits. We should get 0.10 moles per liter. Okay, so let's look at another example here. So it says, for the reaction responsible for the production of ammonia, the initial, so notice they are not giving us equilibrium concentrations. The initial concentrations of nitrogen and hydrogen are 0.32 moles per liter and 0.66 moles per liter respectively. At a certain temperature and pressure, the equilibrium concentration of hydrogen is found to be 0.30 moles per liter. What is the value of K at this temperature and pressure? So this is a combination of what we learned at the beginning of chapter 7, so we looked at the last lesson, to incorporating the K value that we looked at today. So first of all, if you're not given a reaction, the first thing you should be doing is writing out a balanced chemical equation. So we are producing ammonia, so we have nitrogen gas plus hydrogen gas making ammonia. Okay, so we have hydrogen and nitrogen, and then to balance this out, we would need here a 3 and then a 2, and that should be about it. Okay, so because we are dealing with initial concentrations, we are setting up an ICE table, right? So we have the initial for nitrogen as 0.32 moles per liter. Hydrogen is 0.66 moles per liter, and of course we always start off with 0 product. Our change for reactants are negative, products are positive. So nitrogen is going to be negative X because it's a coefficient of 1. Hydrogen is negative 3X because it's in a coefficient of 3, and we're going to have positive 2X down here. So our equilibrium is going to be our initial plus our change, 0.32 minus X, 0.66 minus 3X, and then of course just 2X. Now remember the goal for this is we're trying to solve for K. So let's back this up for a second. Let's write out our K expression. So it's products over reactants.